Hey guys, so in our last video, we discussed how to solve and graph single individual inequalities. And this lesson is all about something called compound inequalities. Now, first things first, what is a compound inequality? Well, a compound inequality is any combination of two or more inequalities joined by either an and or an or. And the strategies we use to solve these compound inequalities are going to be very similar, but they're going to interact with one another, either by being joined by an and or an or, and we're going to discuss how that works right now. So let's take a look at our very first example, where we have a is greater than or equal to -4, and a is greater than or equal to 7. And here's what the strategy is going to be every time. Let's start by graphing each of these individual inequalities first, and then we'll explore how they interact with one another. So for a is greater than or equal to -4, let's do that in blue. We'll have a -4 over here on the number line, and we'll fill it in, and our arrow will go to the right. So any number shaded in blue is going to make this inequality true. For a is greater than or equal to 7, let's do that one in red. So we'll have a 7, we'll fill that in as well, and that arrow also goes to the right. So any number shaded in red will make this inequality true. Now what does this and mean? Well, to be a solution to a compound inequality with and, a number must be a solution to every single one of the individual inequalities connected by and. So in order to be a solution here, the number must make both this inequality true and this inequality true. And if there was a third inequality, it would have to make that one true as well. It's got to make them all true. So let's take a look at our number line. So for instance, these numbers in this region out here to the left, these numbers make neither this statement true nor this statement true, so they're definitely not going to be solutions. Let's get rid of them. These numbers between -4 and 7, well, they're shaded in blue, so they do make this statement true, but they are not shaded in red, so they do not make that statement true. And since they don't make both of them true, these numbers are not going to be part of our solution set. So let's get rid of that. Now these numbers out here, numbers greater than or equal to 7, are shaded in both blue and red. That means they make both this statement true and this statement true. They make all of the statements true, and therefore this is going to be our solution set over here, this region of numbers. Now, how do we tell our reader that? We have to do it in two ways. The first way is to tell them that this is the solution set graphically. And what we're going to do is we're going to shade that region of our number line, just like this. So that tells our reader that these numbers, they're going to be the solutions to this compound inequality and nothing else. But it's also important that we give our reader a written statement of the solution set. And so I would say in this case, it appears that what numbers are solutions? All numbers greater than or equal to 7. So it's important to write again an explicit statement of our solution set in addition to what we've done graphically. All right, not so bad. Let's proceed. So in our second example, we've got 3/2 is less than or equal to a, or a is greater than or equal to 5. So the big difference here, we've got an or. Let's see what happens. Same strategy as before. Let's graph these individually first. So for this one, we'll have -3/2 on the number line. We're going to fill that in, and our arrow is going to go to the right. For a is greater than or equal to 5. 5 is our boundary number. We're going to, again, solid dot, and we're also going to shade to the right. So interestingly, we note that our graph looks very similar to our first one. We have two arrows going to the right that do have a region that overlaps. Okay, but now instead of an and, we've got an or. So let's talk about what that means. All right. To be the solution to an or compound inequality is actually much easier than being the solution to an and inequality. In order to be a solution to an or compound inequality, the number has to make at least one of the individual inequalities true. So if it makes one of them true, it works. If it makes both of them true, it works. The only way to not be a solution to an or compound inequality is to make none of the individual inequalities true. So let's take a look at our number line. These numbers out here to the left of -3/2, these numbers aren't shaded in blue or red. They make neither of these true. These guys are not solutions. All right, let's get them out of here. What about these numbers from -3/2 to 5? Well, they are shaded in blue, meaning they make this statement true. But they do not make this statement true because they're not shaded in red. However, since we're working with an OR compound inequality, that's good enough. If you make one of these guys true, you're a solution to the compound inequality. So a little bit easier with OR than it was with AND. So these guys are going to be solutions in there. Okay, so these guys are solutions. What about these guys over here? These guys are shaded in red and blue. They make both of these statements true, so they're definitely solutions as well. And so, if we want to shade our solution set, all of these numbers are going to be solutions to this compound inequality. And of course, they go on and on forever in this direction. And so there's the visual representation of our solution set. What are these numbers? Well, if I were to state the solution set with a written statement, I would say all numbers such that -3 halves is less than or equal to A. Again, remember, really important to give your reader both a visual representation of the solution set and an explicit written statement. So that's the general way to handle and OR compound inequalities. And so as we make our way through the next examples, I urge you, why don't you see if you can do them on your own or predict what the solution set will be. But of course, I'm going to walk you through them as well. I'll probably go a little bit quicker. All right, in our third example, all right, let's graph the individual inequalities first. I'm going to put a circle at 4/5, and it is not going to be filled in, and the arrow is going to go to the left. And I'm going to make a circle at 9, and it is not going to be filled in, and the circle is again, the arrow is again going to go to the left. Kind of similar to what we did before with that AND statement. The arrows are going in the same direction, except they just happen to both be going to the left now. Okay, to be the solution to an AND compound inequality, you've got to make all of the statements true at the same time. These numbers make neither of them true. These guys are not going to be solutions. These numbers in the middle, they make this guy true, but they don't make this guy true. So, since they don't make all of them true, not going to be solutions. However, these numbers less than -4/5, they make both of these statements true at the same time. Those are going to be our solutions to the compound inequality. So let's go ahead and shade it first. I always suggest using the graph to find your solution set first. And after graphing, that's when you should make your written statement. And I'd say all numbers less than 4/5, those are going to be the numbers in the solution set. Awesome. Very similar to this graph up here. Okay, in our fourth example, here we go. We've got an OR statement, good thing to keep in mind. All right, A is less than -4. So we're going to have a -4 with an open circle going to the left. A is less than -8. We're going to have a number at -8, another open circle going to the left. Okay, very similar graph to what we had here. Of course, this is an OR statement, not an AND statement. So we need to make only one or both of these true, and you'll be good to go. Let's see. These numbers out here make neither of these statements true. Boom, these guys are not going to be solutions. Okay, these numbers in between -8 and -4, they make one of them true. Okay, those guys are going to be solutions, even though they don't make this one true. If they make at least one, they're going to be solutions. And these numbers out here, well, they make both statements true. They're going to be solutions as well. So our solution set graphically is going to look like this. And if we were to make an explicit statement of our solution set, I would say all numbers less than -4. So hopefully you're starting to get the hang of this, and maybe you can proceed on your own now. But of course, I'll walk you through the rest. All right, in our fifth example, same strategy as always. We got to start by graphing the individual inequalities and then seeing how they interact with one another. So there's a 3, A is greater than or equal to 3. 9, A is less than or equal to 9. Oh, interesting. Okay, this is a situation we have yet to see yet, because now we've got arrows going in opposite directions, whereas in every one of our previous examples, they've all gone in the same direction. So now that they're going in opposite directions, well, in order to be a solution, the number must make this statement true and this statement true, because we're dealing with an AND statement. So let's take a look on the number line. Well, these numbers out here make this guy true, but they don't make this guy true. So they're not going to be solutions. Sorry, no luck. These numbers in the middle, they are shaded in blue and red. They make this statement true and this statement true. They are going to be solutions. Awesome, awesome, awesome. Let's keep that in mind. And these numbers out here, well, they're shaded in blue, but not red. So unfortunately, since they don't make all the statements true, they're not going to be a solution. So it appears that our solution set is in this region just here in the middle. And it's kind of bounded, right? It kind of starts at 3 and it ends at 9. And it's everything between 3, and 9. And so here is where the statement of the solution set gets a little tricky. What I would actually say is, if I look at this intuitively, I'd say, well, any numbers between 3 and 9, including 3 and 9, are going to work. And this is how we write it. We write it like this. 3 is less than or equal to a, which is less than or equal to 9. Now, this is a very different statement from any we've made before, and this kind of longer statement of a solution set happens only when we have a solution set that looks like this. It's bounded. It starts somewhere, and it ends somewhere. Usually, like before, all of our solution sets kind of went on forever and ever to the left, or they went on forever and ever to the right, and they had different looking statements of the solution set. But this guy, since it's bounded, since it exists only starting here and ending there, that's why this has a more interesting statement of the solution set. So, just a heads up. All right, continuing on. All right, here we go. Let's graph these individual ones first. So, a is greater than or equal to -7. So, -7. And a is less than or less than -1. Okay. So now we got to say, well, here's the deal. To be a solution to an or compound inequality, if you're shaded at all, if you're hit by red or blue or both, then you're a solution, right? As long as you make at least one of these guys true. And I'm looking at this number line, and, well, these numbers are hit by red. These numbers are hit by red and blue. And these numbers are hit by blue. So that means every single number is a solution because every single number makes at least one of these guys true. And so in this situation, our solution set, you could shade the entire number line if you want. Just going on and on and on forever and ever. And you would say the solution set, this is actually most important, is to write that all real numbers are going to be solutions in this case. So this is another interesting example. And what I would say is, I shaded the number line here to show that it was all real numbers. This is the one time when, if you would like, you don't have to shade your solution set because it is implied by this statement, all real numbers. Every other time, I would really, really, really shade it too. Okay, here we go. More examples. Okay, here we go. Again, first thing I would do, let's graph the individual inequalities. A is less than or equal to -4. And a is greater than or equal to 1/2. So 1/2. Awesome. All right, so now since we're looking at an and compound inequality, we're looking for numbers that make all of these statements true at the same time. We're looking for numbers that are shaded both blue and red at the same time. All right, let's check it out. Well, these guys make this one true, but not this one. Womp womp, not solutions. Okay. These guys make neither of them true, so definitely womp womp, no solutions. Okay, what about these guys? Well, they make this true, but not that true. So womp womp, not solutions. And so there are no numbers at all that make both of these statements true at the same time. There are no numbers that are hit by both blue and red at the same time. There are no solutions to this compound inequality. And so there's nothing to shade because there are no solutions, but it's really important that we write to our reader there are no solutions. And if we use our intuition, I mean, let's think about it. It's impossible to be less than or equal to -4 and greater than or equal to 1/2 at the same time. I mean, it's just not going to happen. So no solutions in this case. All right, and let's see what happens here. All right, so we've got a is less than or equal to -5. Okay, and we also have a is greater than +1. All right, so again, a very similar looking graph. Now we've got two where there's no overlapping at all. And this one's going to be, this one number 8 is going to be a little awkward. And I'll show you why. So for instance, these numbers out here, all numbers less than or equal to -5, they make this statement true, but not this one. But that's okay. There's still going to be solutions because as long as you make one statement true, I'm good to go. So these guys are solutions. These guys, not solutions. They make neither of these guys true. So those guys in the middle, not solutions. And these guys over here, all numbers greater than 1, they make this guy true, but not that guy true. But that's okay, because as long as you make one true, you're going to be the solution to an or compound inequality. And so what's interesting is we have these two different, distinct regions of numbers that are part of the solution set. And so this is very odd. So first things first, let's let the reader know by shading these in that these numbers are solutions and that these numbers are solutions. But you know what? There's no easy way to write a statement of the solution set. it's actually just going to be repeating what the original problem was. But it's important that we do so. And so numbers that are going to be solutions are all those that make these true and all those that make those true. So that's how we have it. So a bit awkward, but hey, what are you going to do? All right, now on to a few trickier examples. They're not going to come up often, but they will come up, and I want us to be aware of them. All right, so a is less than or equal to 5. So here's a 5. A is less than or equal to, oh, this is odd. And a is greater than or equal to 5. So I'll kind of, I don't know, I can't make another circle. I'll kind of shade it half red, half blue. Oops, excuse me. So now what are the solutions going to be? Well, these numbers are not solutions because they make only one statement true. These numbers are not solutions because they make only this statement true. In fact, the only number on the entire real number line that is both less than or equal to 5 and greater than or equal to 5, the only number shaded in blue and red is 5 itself. And so this is a very odd solution set. Our solution in this case is just the number a equals 5. And you can try to shade if you want, but it's kind of hard to shade a number. Just a single number. You maybe put a dot here or something. But this is very interesting that only one number is going to be a solution. Now note to self, if either of these had been maybe less than 5, or this had been strictly greater than 5, then there would not have been any numbers that they had in common. The one number they did have in common, they wouldn't have anymore. So if this were just less than, or if this were just greater than, then we'd have no solutions. Okay, here we go. All right, a is less than 8, or a is greater than 8. So, okay, you can see this is going to be another kind of weird one going on here. So a is less than 8, and a is greater than 8. So this is kind of odd. Maybe we'll do it like that. Okay, and so what do we say? Well, what numbers are going to be solutions here? Remember, this is an or compound inequality, so we're looking for numbers that make one or both of these true, any number that's shaded at all on the number line. Well, these numbers that are less than 8, they make this guy true, so they're definitely going to be solutions. These numbers greater than 8, well, they make this guy true, so they're definitely going to be solutions. And so it looks like maybe all numbers are solutions, but there is a number that is not shaded at all, that is neither less than 8, and it is also not greater than 8. And that number itself is 8. 8 is the only number not a solution to this compound inequality. So how would we write the solution set? Well, first things first, we should shade. So I know we're getting a little bit busy here, but you can still tell the reader, listen, all numbers less than 8 and all numbers greater than 8 are going to be solutions. How do we write a solution statement? This is another one of those kind of awkward situations where we have one region and a different region that are solutions. So you can just write this as a is less than 8 or a is greater than 8. But there actually is another way you can communicate that. And what you can say is a is not equal to 8. And by saying a does not equal 8, you are implying that every number other than 8 is a solution. All right, one final example. And this one is an odd sort of statement. In fact, this statement right here looks a whole lot like the statement we had at the end of number 5, where we have kind of one number is less than a, which is less than another number. And that happened when we had a solution set that was kind of bounded. It existed between two numbers, in this case between 3 and 9. And this is going to be the exact same case with this example in number 11. I mean, if I were to read this statement intuitively, I would kind of read this as a is between -4 and 7. And it includes -4 and 7 because those are both or equal to statements. So one way to handle this is just to kind of go right for the jugular and say, you know what? If a is between -4 and 7, well, I'm going to make a -4. I'm going to make a 7. I'm going to fill these both in. And you know what? Here's our solution set. Boom, we're done. You just write it here and you shade it in and you're done. And well, the statement would be no different from the original one. So that's one way to handle these sorts of longer, slightly more complex compound inequalities. But there is another way to handle these, and whichever way resonates with you, you're welcome to use. So let's look at this one again. And when I look at this kind of longer, complex inequality, I actually see two inequalities buried within it. One of them says that -4 is less than or equal to a. And okay, we can graph that -4 is less than or equal to a, so to the right. But another one says that at the same time, a is less than or equal to b. And okay, we can graph that -4 is less than or equal to a, so to the right. But another one says that at the same time, a is less than or equal to b. And okay, we can graph that -4 is less than or equal to a, so to the right. at the same time, A is less than or equal to 7. Now, if both of those are happening at the same time and they are both true, that means that this must be an AND statement. So that's a really big deal. Now, this AND compound inequality, I bet we can find the solution set. It's going to be all these numbers in here that are shaded twice. And so we see that our shaded solution set and our statement of the solution set are one and the same, as they were for problem number 11. But just a heads up that when you see a long condensed compound inequality like that, you do have the option to split it up into its two component inequalities, and it will be an AND compound inequality. And we're going to discuss this a little bit more in the next lesson. So that's it, guys. I hope you enjoyed, and I hope you found it helpful.